Hello, everyone. In this video, we will give a guide and tips for chapter 26 of my Java book. Chapter 26 introduces AVL trees. In the preceding chapter, we introduced the binary search trees. On average, the binary search tree, the height is out of log n. So that gives you the average time for search, insertion, and deletion at order of log n time. But it's not guaranteed. In the extreme situation, you could have everything in one line in a binary search tree. So that would be degraded into a linear time, order of n time. In this chapter, we introduce AVL trees. AVL trees guarantees that the tree is always well balanced. So in the worst case, the time complexity for search, insertion, and deletion is order of log n time. So let's look at this tree. We're going to define the AVL tree as this. First, we define the balance factor. Balance factor for every node is the height of its right subtree minus the height of its left subtree. So for this all the leaves, the balance factor is 0. So for this one here, 67, the balance factor is 1 because this is height is on the right is 1 more than on the left. So for this 100 is -1 because the height on the right is 1 less than the height on the left. So that's the balance factor. Now, if the balance factor is 0, 1, or -1 for every node, and then the entire tree is balanced, is an AVL tree. So that is the definition for the AVL tree. So how are you going to rebalance it? So we're going to look at if the tree is not balanced, we're going to perform the operation to rebalance it. So if you start with an empty tree, you keep adding the nodes. So at some point, it's not balanced. So what do we do? So this is, we're going to do an operation. It's called rotation. So this is there's 4 rotations: LL rotation, RR rotation, LR rotation, and RL rotation. So let's look at the LL rotation. It is left heavy. So here is, so this we identified, and this A, the balance factor is -2. So that's not balanced. All right, further, on the left side, it is either -1 or 0. So this is left heaviest, left. And the way we perform the rebalance is we do rotation. So this is rotated toward the right. So now you have this B is here and A is a child of B now. So, and there's other ways. And for this RR rotation is symmetric the other way. So LR rotation, so you perform a rotation and there's a slide here. This is A, B, C. So you perform the rotation, and this is C is right becoming here, and this is the B, A are the left and right child of this C. So it's everything is balanced now. This is to performing rotation. All right, so we're going to design the AVL tree as a subtype of BST. So with additional methods. So those are the private methods we need to use to balance the tree, and this is the override, the insert and delete. So when you insert, and it may cause the tree is unbalanced, so you're going to perform operation to rebalance the tree, and same as delete. And this AVL tree now contains the AVL tree node. So this is the same as the tree node. It's a subtype, except that we have one more thing is that, and this is additional data field is height to denote the height of each node here. All right, so here, and this is the AVL tree. It has everything from the inherited from tree node, this element and left and right. And additionally, it has height. We're going to override the insert method. So you're going to insert things right here. We're going to check if this is along the, so this is the along the, this is the path from this new node to root, and we're going to see if there's any node that's unbalanced, and if not balanced, we're going to perform the rotation to balance it. So that is here, it's to perform the balance. All right, so this is the implementation on the one of the rotations. We have 4 rotations. So this is LL rotation, and this here the in the checkpoint, and we write the code for other 4 rotations. So this is to implement the delete method. So after delete it, and the tree may not be balanced, so we need to perform rebalance for that. So this is the complete implementation of the AVL tree. So now we have all this, put all this discussions together in the implementation. And this is to write a code to test the AVL tree. And this is to so analyze the time complexity for the AVL tree. And the time complexity for this AVL tree is out of log n time, and because we can prove that the height, it's out of log n. So this is for search, insertion, and deletion. This is all out of log n time. That is all for this chapter on AVL trees. Thank you for watching. Goodbye.